Today I'm gonna show you how to reproduce the paper that was done here, mainly the parameter estimation and adaptive control for servo mechanism with frictional composition. So these two gentlemen tried to present a new method for adaptive parameter estimation and the corresponding the design control for. So it's an nonlinear servo mechanism, and on top of it, they include the friction compensation. So a continuous friction model is employed to capture the friction dynamics of the servo mechanism. Then there are non-system parameters, including the friction model parameters, are online estimated by a derived adaptive law. So hence a new adaptive law is proposed to achieve a faster and more accurate parameter estimation over classical adaptive laws, so as to suppress the undesired transient dynamic. So an auxiliary filter is used to extract error for driving the parameter. Then so it goes on and how you can find this paper at IEEE. So simulations are given to validate the efficiency of the developed adaptive laws. So this is what this guy trying to say is the proposed control for the PMSM. So they're trying to come up with a way of controlling that. Uh, so first of all, we have to begin by modeling this the server, a servo mechanism model. How then this represents our plant in this case. So this is the structure, the equations that model this the server model. So it uses the permanent magnet synchronous motor. So this is the schematic shown here in figure 1. You can go through it. So we have the PSM, APM, power supply there, PWM, of course, as you know, some kind of driver, clock transformation, park transformation, and all that. Of the inverse park transformation. All these are geared towards modeling the entire permanent magnetic synchronous motor. So this is the equation for that, and also we come down and finally we get this model, which is convolutional this. So this is what, first of all, we model the servo model, this first part. So we need a couple of blocks here. For example, we need some two integrators. We have x1 dot and x2 dot. We have the x2 dot goes into x1 like that. Now we have x2 which are phi over u, like an input. We are given the values here. Phi 1 times also phi 1 represents k1 over g, phi 2 over x2 there. So x2 and x1, x2 represents the velocity, x1 represents the position, or in terms of revolutions. So we have, of course, this equation tan beta 1 over x2 and all that. These are the frictional model parameters, all those lambda 1, 2, and beta 1 up to 3. All of them are described here. And then so we have these parameters that are modeled here. Okay, we have some, you can see the adaptive law, filters operation, and then you have the servo controller commands, now controls the servo mechanism. So from here directly into the servo controller, this is what we intend to achieve. And of course, we give the output as x1 and x2. That's what we're tracking, the speed and of course the position. In this case, they can how many this distance the motor will cover when it rotates, that is the revolution. So all this is what we are trying to achieve. So finite parameter estimation. So first things to model the servo mechanism. So these are the equations, and below here you can find the parameters that are used in the simulations, all that we have there. And so let's begin with that first of all. So not to do the practical practicality part of it, not to validate, we're just doing the MATLAB. So as I said, we need some few blocks here and there. We need the two integrators, some constants, some gains, some products, some addition like 1, 2, 3. Yeah, these are plus, this is the negative, 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 and all that. So you can come and include this one if you want. This one is the opposite of TD. You know that TD, you can do some estimation of it. These are the disturbances. You can either have we can either include or not. So for this one, maybe we'll add. Okay, so we have the minimal disturbances and we have zero disturbances. So we'll capture both of the disturbances that are there. And of course, the friction coefficients are given as follows. So this one can be online updated via this is the lambda 1, 2, and 3 via the adaptive law per se. So question 5, you can see them here, which they are greatly applied for here. So let's start. Let's open up Simulink and show you how this one was done. So as I said again, you need to integrate as the first one and the second one. So you can decide to put it wherever you want. It doesn't matter. You can put it here so that the output of this one fits into the input of the first one and all that. So you can put them for side to side, and the model is the first one is really simple. You just put the first integrator, the input is x2, the output is 1 as seen here. Let me just put this one side by side. Let me just put them side by side. As you can see, you can compare the two Simulink models. So it goes up to get the one, the position, of course, the x2. It has a lot that needs to be done. So here we have the integration. Of course, from here we get past this. So let's model all of this. This part here, it's what we have modeled from here. Everything here. So we first of all add the addition, then we add the 3, the plus, minus, 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 and all that. So K1 plus that, K2 pretty much straightforward. So start slowly by slowly, you add TF. So the last one is TF. You can add TD and all if you want, T and delta, TD, TL, TF, TD, TL, TF. So it's simpler, but I opted to include the delta part as I can see here. But the last one should be TD all, negative except the delta, which is a bit positive, you can see here. So as you can see here, the TD is the negative of TD. So TD is the disturbances here. You can zero disturbances for the first case, minimal disturbances of 0.01 and all that. So we have the manual switch. You can switch either we have zero disturbance or a little disturbances. And of course, I just wanted to rename this signal so that I pass it through a gain of 1, so nothing changes. Here it's just the same value. Against anything. You get the delta, of course, you have the TD and all that. This one Ti is a constant that is also given here. So we model again, we get sum all of those, we put it inside that one. So TF is given by this equation. What you're seeing here above is just a modeling of this equation. For example, let me go through it quickly so that you can be able to see what I'm saying. So here we have the first product. Let me just come back a little bit. So we are taking, we first of all start with the inside before you can, that's how we model something. So start with these two, multiply the beta 1, multiply by x2, you take that one, you pass through a tan h function, and then the next bit, this one is a positive. You do the second one, beta 2 times x2 again, pass it through the tan h, give it a negative after that. the answer that you get after subtracting the first one and the second one, you get multiplied by the gamma 1, that is, as you can see right here. Then we go to then we add this part here by 2 10. So you start with the inside b3, now go to beta 3, you multiply by x2, then you pass through that one, the tan h. Again, after passing through, you multiply by the gamma 2, and then last but not least, you just take that signal x2, you multiply by the gamma 3, which are all the parameters are here, you can find them. And lastly, we add all of them. So we take the first two which are already added here, the first two which are already added, we take that one, these two here, we add this and we add this. So that's what we have right here. This is the first two, the second one and third one we get here. So pretty much, so when you run it, that's what you will be able to see. So let me just do a quick run it. So running for a period of 10 seconds, we output to the scope what we want to see. For example, there is x2, and then there is a x1. So this one represents the speed. So it quickly ramps up to have a upper speed of around 3 point something rads per second there. From there, we have also x1 there position. So it also increases linearly, as you can see. It's expected to behave that way. So say it's about around so for 10 seconds it rests at around 32 or 33 radians per se. And then this one, as I said, it ramps up quickly from 0 to around 3.2 or about, not 3, almost 3. So it levels off because we have from U equals to 1, that is the input voltage. U equals to 1. So it balances the friction load torque, and the net torque goes nearly to 0. So acceleration also 0, so that you can see nothing. Speed is constant. So the steady state speed, this is the point where the applied torque equals to friction plus the load torque, as you can see at this point. So numerically, you are seeing around 3 rads over 10 seconds. So it does not climb any further because the net torque has become 0. So we'll move on to the next part B from this. So thank you. See you in the next.